Hybridization, a blend of atomic orbitals to produce bonding orbitals. With 4 electron domains, such as carbon, which has 4 valence orbitals, 2s2, 2p4, 4 orbitals, and you can see how they would be arranged in the atom. But when carbon gets ready to bond and will produce CH4, all 4 of its valence orbitals will be used, an s and all 3 of the p, and as a result they will blend together to produce 4 equivalent hybrid orbitals that will be tetrahedrally arranged equidistant from each other. If, however, carbon were bonding in the form of CH2O, if you can draw a Lewis structure, you'll see that there will be 3 domains around the central carbon. This time, as a result, carbon will blend only 3 of its orbitals, and s and the 2p orbitals will blend and hybridize to produce 3 equivalent sp2 hybrid orbitals. 3 domains always results in sp2 and trigonal planar. Notice that there will be a leftover p orbital. More on that. What if carbon were bonding with another carbon and 2 hydrogens to make ethine? If you take a look at the Lewis structure, you'll notice that each carbon will have only 2 domains. Thus, only 2 orbitals will be used to produce 2 hybrid orbitals. 2 domains will always result in sp hybridized orbitals, leaving 2 p orbitals unhybridized. Here's a summary of hybrid orbitals. 4 domains. If you can draw a proper Lewis structure, all 4 orbitals will be used, resulting in sp3 hybrids and a tetrahedron geometry of electron domains. If there are 3 electron domains, only 3 orbitals will be used, resulting in sp2 hybrids, resulting in a trigonal planar geometry of the electron domains. Again, with 2, only 2 orbitals will be used. The 2 p orbitals will be left unhybridized. These 2 p orbitals will blend to produce sp hybrid, resulting in a linear geometry of electron pairs. Now we'd like to be able to name bond types. In particular, we want to pay attention to double and triple bonds. But first, the overlap region that occurs directly between 2 nuclei, we'd say this was on the internuclear axis, is called a sigma bond. All single bonds are sigma bonds. However, electrons that end up above and below the sigma bond and are made from these unhybridized p orbitals that were referred to earlier will be called pi bonds. All double bonds are made of 1 sigma and 1 pi. All triple bonds are made of 1 sigma bond and 2 pi bonds. Let's look at what's going on in the formaldehyde molecule. We saw the Lewis structure, sketch it again, and we want to think about how many domains around both the carbon and the oxygen. What are the shape of those electron domains? What's the molecular geometry? What's the name of the hybrid orbitals, and how many sigma and pi bonds? So you see the Lewis structure. Both the oxygen and the carbon form 3 equivalent sp2 hybrid orbitals. And you can tell this because there are 3 domains around the oxygen and there are 3 domains around the carbon, always resulting in sp2. So if I look closely at the carbon, here are the 3 sp2 hybrid orbitals. One of the sp2 hybrid orbitals will make the part of the double bond here called the sigma bond. Carbon will use the other 2 sp2 hybrids to bond with hydrogen. Just as in oxygen, the other one part of the hybrid is used to make the sigma bond, and the other 2 parts of the hybrid orbitals, the other 2 lobes of the hybrid orbitals, will be used to hold the 2 unshared pairs. The unhybridized p from the carbon and the unhybridized p orbital from the oxygen, here and here, will effectively bend and end up overlapping. Let's be clear that this is 1 pi bond. These 2 parts are 1 orbital. So we have the sigma, and the 2 orange parts are the pi bond. Let's take a closer look at N2. What's the hybridization around each nitrogen? Take a look, and each nitrogen has simply 2 electron domains, which will always indicate sp hybridization. The diagram on the left shows the sp hybrid orbitals here, and notice that 1 p orbital and the second p orbital, this is just 2, not 4, the unhybridized p orbitals are shown in blue. The diagram on the right shows that the sigma bond will result from the overlap of the sp hybrid, and the lone pair on each nitrogen is held in the other portion of the sp hybrid. Now let's put these together. The sigma bond is here, the 2 unshared pairs on the outside, using up the 2 sp hybrid orbitals, and the unhybridized p orbitals bend to make 1 pi bond, and the other unhybridized p orbitals bend to make the second pi bond. You can think of the sigma bond as the hot dog, and 1 pi bond as 1 hot dog bun, and the other pi bond as a second hot dog bun. How about benzene C6h6? This is a ring structure with alternating double bonds, which will participate in resonance, as the double bond could be here and here and here, resulting in an equivalent resonance structure. And what happens is, take a close look around each carbon, you'll see 3 domains, meaning sp2 hybrid, which will be trigonal planar, leaving on each carbon an unhybridized p orbital. Those p orbitals will bend toward one another, resulting in pi bonds. Again, let's be clear, this is 1 pi bond, even though there's 2 parts, the hot dog bun above and below. And because of the resonance that occurs, we have a delocalization of electrons above and below throughout the ring. Delocalization leads to more stable molecules.